Hi, everyone, and welcome back to Spaced Out. I recently interviewed Yale Professor Malena Rice about a really interesting type of planet we see in our universe. They're called hot Jupiters. In this interview, we broke down what they are, why we find them interesting, and the theories for their formation. So, to begin, can you tell us a little bit about your journey, how you became an astronomy professor at Yale and how you settled on your specific research interests?
Yeah, so I did not really know much of anything about astronomy until I became an undergrad. So I was pre-med I
Oh,
just thought I was going to be a doctor for pretty much my whole life. And I got to undergrad and I took this biology class and I just couldn't do it. I was like, I need to drop this class. And that means I can't be a doctor. So what am I going to do now? So I had a friend who over a late night conversation in my dorm my first year convinced me to just try astronomy till I got bored. And so I did. And I decided to just keep going until it wasn't fun anymore. And so have just continued ever since, which has been lots of fun. Yeah. And I guess you specifically asked how I became a professor, which is really kind of just a continuation of
yeah.
that. I knew that the thing after, if I wanted to keep doing astronomy after undergrad, was to apply to grad school. So I went to grad school. And then at the end of grad school, I got the advice that it was a good idea to apply to dream jobs early so that you get some practice and you have a good sense for what it's going to look like when you do it for real. So I applied to the Yale faculty job and somehow it worked out. So it ended up working out a lot faster than I expected, but I've been really happy with it. Like, I feel very, very fortunate to be where I am today.
Yeah, oh, that's great to hear. So, how did you settle on like planet formation and these type of weird planets that you say you focus on?
Yeah, I love learning about planets that are super different from anything that we've ever seen before because I think that they give us this really cool insight into what else is out there in the universe. Like we have all these things that we're kind of familiar with, but I love digging into like things that we've never seen before, things that just make you think totally outside the box and that really kind of stretch your imagination. So those are the kinds of planets that really capture me as the ones that make me think totally differently and just imagine like, wow, what would a world be like that is so, so different from anything that we've ever really encountered before.
Oh, yeah, that's so cool. So, the questions in astronomy, I guess, that you're interested in, as you've said, are helping to like piece together these ideas, these planets that kind of challenge our current notions of what we expect to see. But how do you consider a planet to be weird? Like do you just pick one that doesn't really fit into our solar system, or is there some other criteria you kind of use to determine what to study?
Yeah, I would say I don't necessarily compartmentalize myself to only work on weird planets, but
Mhm.
the ones that I think that I would define as being weird are the ones that kind of challenge our solar system centric formation theories. So that doesn't necessarily mean that they need to look exactly like the solar system, but we have this kind of idea that the solar system formed from a disk of material. There was sort of more material in certain parts of the disk. The temperature was different at different points in the disk, and that's kind of what led to these four little planets in the inner part of the system, four bigger planets in the outer part of the system. And they're also on these orbits that are kind of nicely aligned or pretty close to aligned with the way that the sun spins. So there's actually a little tilt. So the sun is tilted by 6 or 7 degrees relative to the rest of the planets, but it's a pretty small
Yeah.
tilt. Everything kind of like pretty much rotates together.
Mhm.
And when we look at exoplanet systems, there are so many deviations from this picture. And so yeah, I think the ones that I would say are weird and confusing are the ones where, we had this idea. We were like, we've got it solved. We know how the solar system formed. And then we found exoplanets and it just totally smashed that entire vision, which is incredible. It's so cool when you have to just revisit and go back to the drawing board like that.
Yeah, it's like a puzzle almost, right? Where every system is like a new piece. It's very interesting. Yeah. So today we're going to be talking about a particular like weird planet that doesn't really fit our ideas. They're called hot Jupiters. But before we dive into what hot Jupiters are and what they can teach us, Could you really quickly walk us through why we don't expect them to be where they are, like how our own solar system formed, why we have these rocky planets closer in and these giant gas planets further out?
Yeah, so we think that, at least from our solar system centric theory, and you can try to extend this to some extent to exoplanet systems, that uh, especially massive planets form most efficiently kind of where there's a lot more material that's available. And so there's this idea called these ice lines, where it's
Mhm.
basically saying, you either have gaseous material at a certain temperature, or you're able to have rocky material when it's a little bit colder, and you're able to condense that material into something solid. So in the outer disk, when you're far away from your star, it's cold and you can get lots of denser material, and it makes it easier to accumulate to make really big planets in short time periods. So that's kind of why we think that we have these giant planets that are further out. And it is probably pretty hard to make those very close into the star because it's just gas. Like you don't have a lot of high density stuff that's in that area to work with to make really big planets before your disk goes away and you can't really form planets anymore.
Okay, cool. So, how common is our solar system then? Like we've kind of refined or understood the idea of how our solar system forms through these ice lines and snow lines and things. But when you look at other planetary systems, like how often do we really see ones that look like ours? Are there other sort of patterns or systems that are more common?
Yeah, I would argue that we haven't seen anything particularly like the solar system yet. And that doesn't mean that they don't exist. That is really just that we're really bad at finding solar system analogs. We're really good at finding other kinds of planets. And it's actually such a gift that the universe has given us all these planets that are very unlike the solar system, because if all of them looked like the solar system, we
Yeah.
may not have found exoplanets by now. I don't know that we would have put the resources in to actually find them. So yeah, we haven't seen anything really like the solar system yet, or not convincingly so. We've seen Jupiter-sized planets. You can find around like 10% of sun-like stars. So
Yeah.
they exist, not super, super rare, but like how often do you find an Earth-like planet around a sun-like star? That is a number that gets thrown around, and you can pretty much put any percent on that likelihood at this
Yeah.
point. It's really not very well known because that's just something that we're not very sensitive to with our current instruments.
Cool. Um, so now on to hot Jupiters, I guess. So what are they and why are they called like Jupiter specifically? And why do astronomers find them so fascinating compared to everything we just talked about?
Yeah, I love hot Jupiters. They are so weird.
Yeah,
So
obviously.
these are they're hot, high temperature, really close to the star,
Mhm.
and they're Jupiter sized. So they're giant planets that have like these big gaseous, like hydrogen helium envelopes. And they are so strange because I mentioned we think that giant planets must form a bit farther out. You've got solid material where it's cold enough to condense things. So that's sort of far away from your host star. But hot Jupiters are like right next to their host star. In fact, some of them are probably actively falling into their star. So they're really, really close, like way closer to the star than Mercury is to the sun. And they are really puzzling because we don't think that planets that big can actually form that close to the star, or you have to kind of really, really mess with your models to make that something that could ever happen. And so then there's this big question of how did you get these enormous planets that are just right next to their star? Like how could that possibly ever happen?
Yeah, it's really puzzling. And so I guess people have come up with a lot of different theories to talk about it. Um, I guess some that's floated around are like they actually can form there, though that's kind of disagreeing with our understanding of our solar system. But what what do you think? Like, what are the main theories of how these planets got so close to their stars? And are any of these like particularly favored, like fit in kind of with what we see theoretically and with simulations?
Yeah, so part of this really is just a question of what you mean by forming next to the star. And this is language that we use that
Yeah.
we confuse ourselves with the language
Yeah.
that we use sometimes, because you can make like a big core that's basically, a bigger version of Earth, like a super Earth-sized planet that's multiple times the size of Earth, and then have it drift in, and then you can accrete the rest of the material close in potentially. So that's one idea that's sort of forming in place where you didn't have a Jupiter before, but you also kind of had a planet that you
Okay.
drifted in from
Yeah.
outside the system. Or you could have all the gas accumulate. You could basically make your Jupiter-sized planet in the outer system and then have it drift in somehow
Okay.
um, within the disk while your disk is still there. Or you can have your fully formed planets after everything is formed, your disk is gone, you sort of have an analog of the solar system. Oftentimes things will get unstable, like right as you're dispersing the material that your planet's formed from, and you're kind of getting to your final settled state. And in that process, you might have different ways that you can launch your planet onto a very elongated orbit, and it will end up sort of in spiraling. So it gets really close to the star at some point in its orbit, and then it ends up being able to kind of get rid of energy very efficiently at that point in its orbit and in spiraling to become this very close orbiting planet in the end. And that one, even though it probably sounds the craziest, like the other ones sound like, oh, you just, have the planet drift. That seems reasonable. That last one, there are a bunch of different lines of evidence that seem to keep pointing towards it. And this is called high eccentricity migration. It's like this
Mhm.
crazy thing where it's like planets are throwing each other around and they're kind of forcing each other onto these really weird orbits. And maybe it happens sometimes. That's one of the ways that you might be able to get a hot Jupiter.
Okay, so you're saying in that one, like the planets are in really crazy orbits, but somehow when they get close enough to the star, they're actually like trapped into a new one that keep it in the spot that we observe them today. That's the theory. Cool.
Yeah, yeah. So every time they get really close to the star, they get really kind of warped. So it's just
Yeah.
sort of like what causes tides on
Yeah.
the Earth is the moon is warping the Earth and it's kind of like
Pulling.
squishing it. And
Yeah.
so that's happening with the planet too, and that changes its orbit and it can force it to get onto this very different orbit from where it started on.
Wow, that's so interesting that someone just came up, like we came up with that. That's very creative.
Yeah. Yeah, it's great. I mean,
Yeah.
that's what exoplanets are all about. It's like, whoa, how did that happen? And then you
Yeah.
just wildly speculate until you figure out something that could actually work.
Mhm. So, yeah, like help understand this. Your group has kind of compared hot Jupiters to warm Jupiters to understand their formation. So, like, do these comparisons help solve the puzzle or at least add some more insight?
Yeah. If you look at different classes of planets that are kind of
Mhm.
almost the same, but not quite, then it can help you to try to piece together this puzzle of how some planets form differently from others. And, there's this general question of if you just roll the dice, do you get random planets? Do you get totally different planets? How are the different ways they can migrate? And what are the common pathways to get certain kinds of planets versus are some more common than others? So if you look at warm Jupiters, these are really similar to hot Jupiters, but slightly less hot. So the name does a very good job in this
Yeah.
case, just on slightly lighter orbits. But they're really distinct. So they have a lot of neighbors. They have a lot of other planets near them. So if you find a warm Jupiter, you usually find it with other nearby companions. And that's not true for hot Jupiters. Hot Jupiters tend to be pretty isolated and they are kind of alone, which is part of this idea of maybe they must have migrated in some disruptive way that could have gotten rid of other planets.
Yeah.
Um, and the warm Jupiters are also on these orbits that tend to be kind of nicely aligned with the way that the star spins. So in the solar system, again, we see the planets are orbiting basically in the same direction that the sun is spinning. So everything's kind of spinning together.
Mhm.
If you look at hot Jupiter systems, a lot of them are on really weird orbits where they're going sideways or backwards or on sort of crazy orbits relative to the way that the star is spinning.
I see.
And that's not true for the warm Jupiters. And so, what that might mean is that the hot Jupiters are undergoing like some other weird mechanism that's kind of bringing them in, that's flipping around their orbits, that is getting rid of any other planets in the systems. And that's not happening to the warm Jupiters. They seem to be much more like they form in a much calmer environment. That might be a bit more pleasant for other life
Yeah.
and such things of those systems. So they seem pretty distinct, and that is
Mhm.
nice for sort of parsing out, okay, so there are different things, different mechanisms that had to form each of these classes of planets so that you ended up with certain characteristics in one class versus another.
Cool. So you find like a close kind of analog of the system that you want to study and figure out what could be causing the differences.
Yeah, yeah, you can look at either individual systems and you can say,
Mhm.
like, I
Like
know this
on
system
the
really
planet.
well, and
Yeah.
I will figure out like how it could have possibly formed. Or you can look at like a full group of systems and
Yeah.
say, the population, then how can we reproduce this? How can we make so many of this kind of system and so many of this other kind of system given the same universe that we all came
Yeah.
from?
Wow, that's so cool. And your research, your like re most recent work, I guess, about hot Jupiters that I've read at least, suggests that binary stars could actually each host a hot Jupiter, like twins almost. But how can the second star make that happen? Like, do most hot Jupiters actually end up forming in binary systems? Is that what we see?
Yeah, so this is really fun. We have no idea. We have not really been checking.
Oh,
And there's this one system that I've just been stuck on that I discovered existed about a year ago. It's been known for over a decade and nobody ever talks about it. WASP 94 is like the coolest system. It has two stars that are really similar sizes and they both have a hot Jupiter around them. And hot Jupiters are actually really rare. So I mentioned they're weird planets, which is both in the context of they're very different from the solar system, but we also only see them around like 1% of stars. They're not very common. And this one system has two of them, which is crazy. How did that happen?
yeah.
So, so I got really stuck on this idea, and there are a lot of ways that you could form them. You could say, oh, well, both stars formed in the same environment, they formed together. Maybe the same mechanisms of like in the disk migration or something could have happened for both of
Yeah.
them. Or there was a student in my group who showed that there's this kind of cool mechanism that has been proposed as a way to make hot Jupiters where if you have multiple bodies in the systems, you can sort of have your extra star stretch out your orbits and kind of flip them around. And you can have that happen for planets around both stars in the system at the same time. So this is kind of this mirrored effect of you have the planet on one side kind of warping the planets from your primary star, and then in the other system, if you have the same kind of planet that
Yeah.
formed, you can also have exactly the same thing happen. So we often, in these binary star systems, we'll just focus on planets around one of the stars, and then we don't necessarily check for planets around the other star. So we actually have no idea how common these double hot Jupiters are observationally. And we're just starting to actually put together some theories for how you can make those and also make some predictions for depending on how you form your hot Jupiters, do you expect to have a lot of double hot Jupiter systems or not? And
Yeah, that
so
would
that's,
be cool, like statistics to do, to figure out
yeah.
maybe that's how they form in the end is with another star. Um, and like your work could show that. That's awesome.
Binary systems are so fun because
Yeah.
they're kind of like nature's control sample because we don't get the luxury of doing things in labs most of the time. Like everything's so far away. You just have to sort of watch it and then try to figure it out from very, very far away.
Yeah.
But in binary systems, your stars form in the same environment, especially if they're about the same size, then you can say they pretty much form the same way. And then there's the question of okay, well, do you get the same kinds of planets? Do you not get the same kinds of planets? And we don't know. We just
Yeah.
don't have that answer right now because we haven't really checked. And that's something that I think is going to be a really fun new frontier.
Yeah, definitely. And do you think there are still big surprises ahead for hot Jupiters? I guess you can't really say now, but what about other really unusual planet research that you're interested in? Oh, sorry. Can you hear that? The siren?
I can't hear the siren,
Okay.
no.
I'll just repeat. So, do
Yeah.
you think there are still big surprises ahead for hot Jupiter research or really any other unusual planet research? The kind of discoveries that might force us to kind of rework our theories again? Or is that just something you look for in the data and you see and you present and think about?
I think there are probably going to be a lot of big surprises ahead. And that's kind of the fun thing about surprises is you don't really know what they're going to be. They end up coming out and then they just sort of invert your reality and you have to just accept what the universe is giving you and try to figure out what it means. I think hot Jupiters are getting better studied. And so I want to think that we're close to solving the mystery of how hot Jupiters form. But every time I think that, something throws a wrench in my understanding of those
Yeah,
planets. So I don't think we fully figured it out yet even. And that's the oldest question in exoplanet science. The first exoplanet that was found around a sun-like star was a hot Jupiter. And like it was a really significant discovery because people didn't really think to look for them because it seemed so crazy that they would ever exist. So yeah, I think there's probably a lot that remains to kind of be discovered. I think there is going to be a lot of cool science coming out about like free floating planets, for example, with the upcoming NASA Roman Space Telescope. That's going to be really fun, just figuring out how many rogue planets are just floating around in the galaxy with no star that they're attached to.
yeah,
So that I think will be really cool. And just looking at smaller planets, looking at planets of kind of different sizes, different orbits, there's so much that we don't know.
yeah,
Mostly at this point, we know certain kinds of planets exist, and that's about it. Like we're starting to just barely scratch the surface of, what could they be made of? How did they form? How did they migrate? But there's really so much left to be discovered because this field is so young. It's only 30 years old. There is
yeah.
so much that we still don't know about planets, and that's what's so exciting about them.
Yeah, I guess I was thinking about like the search for life even and how people are starting to like look for life they might not even exist because it's really hard to find what we think traditionally of what life should be. And I feel like exoplanets are the same way. Like there might be classes of planets that we're not even looking for because we don't even like have an understanding of what it could be. It's kind of
Yeah.
cool stuff to think about.
Yeah. Yeah, the search for life is tricky. It's hard to define what life would look like and
Yeah.
how we would actually be able to tell that it's life. So that's a fun question. I do not have the answer.
There's always analogs to everything here, which is cool.
Yeah.
Okay, well, thank you so much for agreeing to do this. It was so exciting to learn about your understanding and your work on hot Jupiters as well as what they are. So, thank you again.
Yeah, thanks for inviting me. Great to chat.